In 7.2 Part B, we are going to talk about some applications of radians. And the first one we're going to talk about is arc length. Let me write this formula a little bigger. So the arc length formula is S equals R theta. Now let's talk about what each of those things are. This is the central angle measure, but to use this formula, it must be in radian measure. And then this is the radius of your circle. Now this formula is completely related to the fact that the circumference of a circle is 2 pi r, and there's 360 degrees to go around the circle and all of those things. But this is just a way for us to measure arc length using radians. So S equals R theta is a formula that you should know. So here, let's look at an example. So I'm going to write down that formula. It says find the length of the intercepted arc in the circle with a central angle measure of pi over 3 and a radius of 4 inches. And we're going to round to the nearest tenth. So I'm going to draw in my radius. And then I am going to draw a central angle. Now, pi over 3, since a pi worth of radians is 180 degrees, 180 divided by 3 is 60. So I'm going to approximate what 60 looks like. And that would be R theta. So if we apply the formula we saw before, we're going to do our radius of 4 times our radian measure, pi over 3, and we are going to get an answer of 4 pi over 3 inches. Now that's our exact answer. If we were to put that into a calculator, you would just do 4 times 3.14 divided by 3 and round to the nearest tenth. Now those would be inches, so that would be 4.2 inches. So they are talking about the length right here that I've highlighted. That is the length of the intercepted arc. Now let's do another one. Now the difference in 4A and 4B is the fact that we have been given the measurement of our angle in degrees. Now remember, the formula S equals R theta is only going to work if R theta is in radians. So let's take care of all those things at once. So let's mark our radius as 7 centimeters. This is approximately 90. So 125, let's say, is something about like there. Now, 125 degrees, if you tack on a pi and put it over 180, you are going to get radians. So before we proceed in our formula, we have to have it in radian measure. So just tack on a pi, put it over 180, and we get that this is 25 pi over 36. Okay, so remember our formula. The arc length is R theta. So our radius is 7 centimeters. Our radian measure is 25 pi over 36. Now, because we are rounding to the nearest tenth and we are getting that exact answer, you can just put 125 pi over 180 in that spot. But let's do it. The exact answer would be 7 times 25, or 175 pi over 36. But they wanted us to round to the nearest tenth, so that means the calculator is our friend. So if we do 175 times pi divided by 36, and then round to the nearest tenth, we get 15.3. And if it starts with centimeters, you better label it as centimeters. So that is how we find arc length, whether we start out with radians or we start out with degrees. That's how you could use that. Now let's talk about linear speed and angular speed. Linear speed is the arc length we have traveled, so a length we have traveled per unit of time. So it's going to be that arc length over time. So that S, we could also say, since S is r theta, that's r theta over t. Now for angular speed, we are always going to use kind of this weird, very rounded W. That is the Greek letter omega. Remember, Greek letters are used a lot to denote angular measure of some sort. So this is radians per unit of time. So theta over time. You can see theta over time is right here in the formula. So velocity, or linear speed, is going to also be, we get one other alternative, it's r times omega. So there are three ways we can do linear speed. It's the hardest one, really. Angular speed is radians per unit of time. Now, some things about angular speed. One rotation is always 2 pi radians. So that is going to help us when we're doing angular speed. Okay, so these are the formulas that you need for linear and angular speed. Now let's look at some applications. So we have a record with a diameter of 30 centimeters. Now that's your typical large vinyl record that you put to spin at 33 1/3 revolutions per minute. So I'm just going to mark this with a 30 centimeters. And I know that because omega is angular speed, this revolutions per minute is going to help me. So I know it's traveling at 33 1/3 revolutions per minute. So that is really important. Okay. It says find the angular speed in radians per minute of the record as it plays round to the nearest tenth. Well, one revolution is always 2 pi radians. So to change revolution into radians, all we got to do is multiply by 2 pi. So omega is just going to be 33 1/3 times 2 pi radians every minute. Every loop is 2 pi. So 33 1/3 loops around is going to be 33 1/3 times 2 pi. Now 33 1/3 times 2 and times pi, rounded to the nearest tenth, is 209.4 radians per minute. Now, I like the exact answer, that 66 2/3 pi radians per minute, but the instructions say round to the nearest, use 3.14 or your pi button on your calculator. Now we've got that same record, 30 centimeters. It's going, what was it, 209.4 radians per minute. Let's write all that down. Okay. And then it says this time to find the linear speed at the outer edge. So what we're talking about is if we put a little mark on the outer edge of our record as it turns, how fast is it going in centimeters per second? So let's go back up and look at some of the formulas that we had from before. So look at our linear speed. So linear speed is arc length over time, which was r theta over time, or which was r times omega. So we can use any combination of those two things to find linear speed. Or really, how or what length, I'm sorry, is it traveling per unit of time? Okay. So we already know it's going 209.4 radians per minute. That was an easy one to do. We just multiply the revolutions by 2 pi. Great. But now it says, what is the linear speed? So remember, linear speed is either arc length over time, r times theta over time, or r times omega. Well, we already have the omega. This is our omega. That's radians per minute. So if we want to find out the velocity, we just have to multiply that by the radius, 30 centimeters. So our velocity is going to be 209.4 radians per minute times 30 centimeters. I kind of did it in the reverse order. There's your radius, there's your omega. Well, if we do that, we get that it's going 6,282 radians. Oh, I'm sorry, the radius length, centimeters every minute. Okay? So if you know the revolutions per minute, multiply by 2 pi, you get radians per minute. If you multiply that by the radius, you get the length per unit of time. Now, one other thing we have to do is all of these things before were per minute. Let me go back here for a second. They said radians per minute. Okay. Here they said centimeters per second. So you might recall back in one of your science classes to change this to seconds. There are 60 seconds in 1 minute. We got to do the reverse of that. Here, let me write it a little nicer. We want the minutes to go on top so that they'll cancel out over 60 seconds. So if you gave me this, you're 90% there. Here, you're going to convert the minutes to seconds by dividing by 60. So if we divide our original 6,282 by 60, rounded to the nearest tenth, that is 104.7 centimeters every second. So watch your units. They might play games a little bit with our units. So that is example 5B. Let's take a look at example 5. We have a carousel that is 6 feet in diameter, and it rotates at 10 revolutions per minute. It says find the angular speed. Remember, angular speed is just radians per minute. Remember, 1 revolution is 2 pi worth of radians, so you just multiply by 2 pi. So that's going to be 10 times 2 pi, or 20 pi radians per minute. Now, they didn't say round to the nearest, so I like just leaving that pi in there when they don't say otherwise, because then that is our exact answer. We found how many radians it is traveling per minute. You don't even use the 6 because the angular speed is what angles are it sweeping through in per minute, okay? Last formula is the area of a sector. I've written it a little bigger here so you can see it. It is 1/2 r squared theta. R is still our radius. Theta is still our radian measure of our central angle. So let's find the area of the sector given. So I'm writing down the formula for you. 1/2 r squared theta. So in this particular circle, they have told us that our radius is 5 meters. That's the r. Our theta is 3 pi over 4 radians. It has to be in radians. If it was degrees, we would have to tack on a pi and put it over 180. So let's put into our formula. So that's going to be 5 squared times 3 pi over 4. And it would be square meters because it's an area. Well, if we do all that, you get 75 pi over 8. And that's your exact answer. And I'm okay you stopping there, really, because I know you know how to put that into a calculator. To put it into a calculator, just do 75 times pi divided by 8. And we're going to get 29.5 square meters. Now, I like stopping here. If they say round to the nearest, put it into a calculator. Otherwise, feel free to just leave that pi sitting on your answer. Oh, well, okay. Anyway, I was doing good too. Okay. So let's do one where it was in degree measure. Remember our formula, area equals 1/2 r squared theta. In this particular circle, our radius is 8 feet. Our theta is 60 degrees, but I don't like that. Tack on a pi, put it over 180, so it becomes radians. Now, you really don't have to reduce it. 60 does go into 180 exactly 3 times. It is pi over 3. If you put 60 pi over 180 and then reduce it later on, that works as well. But our area of our sector is 1/2 r squared times theta. And so if we got the exact answer, we would have 64, but there's a 2 on the bottom, so we can reduce it. We end up with 32 pi over 3. If we end up putting that into a calculator, we get 33.5 square feet. So be careful if it's in radians or if it is in degree measure. So then your homework is as follows. So that is what you want to be working on. There you go.